everyone. Thank you for joining me today. I'm very honored and glad that I could share the talk with you at Percona Live. Today, I'm talking about how we build a geodistributed database with low latency. Let me introduce myself first. This is me. My name is Ming Zhang, and I'm a developer from PinCap. Also, I'm a committer of TiDB at Circle Info SIG, and you can find my GitHub ID here. Let's take a look at the agenda of this talk. Firstly, I'll talk about the geographic problem in databases. Then I'll introduce our distributed database, TiDB. Next is the approach how we solve the geographic problem in TiDB. At last, there is a QA part for anyone who has questions. So please drop your questions in the Slack channel, and we'll answer them after I finish the talk. At first, let's talk about the geographic problem in databases. So why do we need multiple geographic regions? There are several reasons. The most significant one is a database across multiple regions can improve access locality, which can achieve low latency. Secondly, it also improves availability. For example, even if the database in AZ1 is down, the application from AZ1 can still access the remote database in AZ2. However, there are some problems in geographic regions. It's always a trade-off between latency and consistency level. For example, MySQL supports several replication approaches. Async replication has low latency, but it sacrifices consistency level. For semi-sync replication, it sacrifices latency. Group replication is not optimized for multiple geographic regions. Fortunately, databases nowadays have some approaches to solve geographic problems. Our distributed database system, TiDB, also has some solutions. Before digging into the solution, let me introduce TiDB at first. TiDB is an open source distributed NewsCircle database. It is capable of hybrid transactional and analytical processing, aka HTTP, and TiDB speaks MySQL protocol. There are some characteristics of TiDB. It's horizontally scalable, it's highly available, it keeps strong consistency, and in most cases, it's compatible with MySQL. Here's the architecture of TiDB. For brevity, I only introduce the OLTP part and skip the OLAP part because it's not related to this topic. As you can see, TiDB has three major components: stateless circular TiDB, distributed KV storage engine TiDB, and a placement driver PD. All these components are highly available. TiDB is responsible for processing user requests. TiKV stores data and uses Raptor to achieve strong consistency between replicas. PD allocates timestamp for transactions, and it can also perform load balancing and hand failures. Let's talk about the storage part at first. Data on TiKV is organized by regions. Each table is split into regions, and each region contains a range of continuous data, which is typically 69 megabytes. One TiKV instance stores multiple regions. So how do read and write work in TiDB? Each region is managed by a reft group. A region has multiple replicas which are stored on different TiKV instances. All replicas of a region form a reft group. The raft group uses multi-raft consensus algorithm. It contains 3 rows: leader, follower, and learner. When TiDB writes data, data is written to the leader as logs, and then the leader replicates logs to followers and learners. Logs replicated to majority voters are committed. Otherwise, the logs won't be committed and write fails. When TiDB reads data, it reads from the leader because the leader always has the latest data. Let me introduce the transactional model, which is quite typical for NewSQL databases. Since TiDB is a distributed database, it uses two-phase commit algorithm to commit transactions. Firstly, TiDB requests a start timestamp from the PD leader, and the timestamp is taken as the identifier of this transaction. Let's call it start_ts. Secondly, TiDB may read TiDB with start_ts, do some computation, and then pre-write data to TiDB, and waits all TiDB for return success. Then TiDB requests a timestamp again from the PD leader, which is called commit_ts. It's used for committing. And last, TiDB commits data on TiDB, and each version of data is attached with the commit_ts. Since the commit_ts is attached, the data has multiple versions, so TiDB supports multi-version concurrency control, and the highest isolation level is snapshot isolation. I've introduced the internals of TiDB. Now let's see how does GeoDistribution work in TiDB. Before introducing the solutions, let's see what problems may happen in TiDB. Suppose there are 2 zones, AZ1 and AZ2. One client in AZ2 wants to write some data, but the leader is placed in AZ1. The request must cross different zones, which brings high latency. Besides, the leader has to replicate logs to all the followers, which also brings high latency when one follower is in another AZ. But it's fine in most of the time because the majority of the followers reside in the same AZ, and the leader returns access as soon as the majority followers return. The situation for reading is quite similar. The request from TiDB to TiDB also crosses different zones, so it also brings high latency. As you may see, there are some geographic problems in TiDB, and TiDB had tried some solutions before. The original one is bidirectional replication. It means the database is split into multiple TiDB clusters, and the clusters reside in different zones. Clusters replicate to each other by sync tools. The biggest problem is users suffer from maintaining multiple clusters. So what do we want really? We want to maintain only one TiDB cluster, and we want to write and read with low latency. And at last, we still want the cluster is highly available. Let's get to the new solutions, which are the key points in this talk. The first solution is placement policy. Generally speaking, placement policy provides an approach where you can define the placement and replicant of data through circle. So what you need is just writing a statement that TiDB will schedule the data to the zone as you want. There are some scenarios where you can apply placement policy. For example, you can place data across regions to improve access locality, which is the key of GeoDistribution. And you can also limit data within its national border to guarantee data sovereignty. And there are many other scenarios, but we'll skip them today. The scenarios may sound abstract, so I give you a user case. Imagine there is a user management system whose users are distributed over the road. And the users can visit their own information through this system. Here's a typical deployment. There are 2 data centers located in 2AZ, and each application collects to the nearest data center to reduce latency. Users will connect to the nearest application. So our solution is to store each user information in the nearest data center according to the location, and then locations request user information from the local data center. This whole process avoids cross-region requests. To achieve that, the first thing you need to do is to configure the topology, because each component is to recognize the other instances in the same AZ. You can mark each instance with a label. In this case, the label name is zone. All the TiDB, PED, and TiDB nodes are marked with zone equals west label, so they know each other is in the same zone. After you have finished the configuration, now you can define placement policies through statements. Here's an example.
Sample
First, you create a table named user. The table contains information for each user. Then you partition the table by the country of each user. So the users from East countries are partitioned into East, and the users from West countries are partitioned into West. Then you can define the placement policy of both partitions. Here, you define the leader of partition East to stay in the zone East, and leaders of partition West into the zone West. Now let's take a look at the final topology. The leaders are separated into 2 zones. The leaders of East are in the zone East, and others in the zone West. As you can see, one follower replica might still in another zone. This is because the system can guarantee high availability. When a client visits the information of an Eastern user, it requests directly from the leader, which locates in the same zone, so we can achieve low latency. Now you may wonder, how does placement policy work? I will introduce it briefly. After the user requests defines placement policy, TiDB generates some placement rules according to the policy, and then sends them to PD. As PD is responsible for scheduling data, it can schedule the roles by sending schedule commands to all the TiDB instances. Here's what placement rules look like. Each rule contains these elements. As a table partition is a range of data, TiDB can transform it into key range. And combined with left row and constraints, the PD is capable of scheduling. Although TiDB can access data locally through placement policy, there is another problem, which is the latency of requesting timestamps from the PD leader. As mentioned earlier, the timestamp can only be allocated from the PD leader. In this example, the TiDB node in AZ2 will visit the PD leader in AZ1. So the request crosses different zones. What's worse, a transaction needs 2 timestamps. That means the latency will be doubled. So we introduced local transactions. Before going further to our solution, let me introduce two concepts: a local timestamp allocator and a global timestamp allocator. Firstly, each zone will elect one timestamp allocator, which can be either a PD leader or PD follower. In this picture, the PD follower in AZ2 is the local timestamp allocator. Besides, there is a global timestamp allocator for the whole cluster, and it is always the PD leader. In this picture, the PD leader is both the global timestamp allocator and the local timestamp allocator for AZ1. Both local timestamp allocators and the global timestamp allocator are capable of allocating timestamps. And then TiDB can request timestamps from the local timestamp allocator, which saves cross-region access. Those transactions are called local transactions. In this picture, the TiDB node 1 requests timestamp from the PD instance in AZ1, and TiDB node 2 requests timestamp from the PD instance in AZ2. Local transaction may look simple to you, but there are some limitations. Firstly, there may be clock bias among timestamp allocators, which means when TiDB nodes from different zones access the same data, it will violate non-reusability. So to conform to non-reusability, local transactions can only visit local data. And to define which data is local, placement policy is applied. However, there are some scenarios where transactions have to cross different zones to access data. And some transactions need to access global data. For example, DDoL will always access metadata, but metadata cannot be partitioned. So we introduce one more kind of transactions, global transactions. Generally, if one transaction requests timestamp from the local timestamp allocator, it is a global transaction, and the timestamp is called global timestamp. To conform to non-reusability, we need to guarantee that when allocating a global timestamp, the previous local timestamps must be smaller than the global timestamp, and the global timestamp must be smaller than the later local timestamps. So the timestamps are all in order. I've described the concepts and rules which global transactions must conform to. Let's see how do they work. Firstly, the global timestamp allocator collects maximum timestamps, which are allocated already by all the local timestamp allocators. Let's call it local TS. Once the global timestamp allocator has gathered all the local TS, it calculates the Tmax for the cluster, which is the maximum local TS plus 1. So Tmax stands for the max allocated timestamps for the whole cluster. The next step is the global timestamp allocator broadcasts the Tmax to all local timestamp allocators. And once a local timestamp allocator has received this Tmax, it updates their local timestamp starting points. The new starting point local TS is calculated from the maximum of Tmax and the current local TS. You may wonder, why do we need to compare them again? Because the local TS here might be higher than the original one, since the local timestamp allocator continues allocating timestamps, the start point has increased. The The next step is the global timestamp allocator allocates timestamps from Tmax, which means Tmax becomes the starting point for the global timestamp allocator. As for the local timestamp allocators, they allocate timestamps from the new local TAS. Now, Tmax must be higher than any local timestamps allocated before, and the local timestamps allocated afterwards must be higher than Tmax. So all the timestamps are in order, and the cluster conforms to non-usability. I've described how local transactions and global transactions work, but obviously they have some limitations. For local transactions, the data must be bound to one AZ, and a local transaction can only read or write the data from the current AZ, which is not enough for some situations. For global transactions, they're able to access any data. However, one request will cross regions 3 times for allocating just one global timestamp, which is very expensive. So global transactions are rarely used. They're typically used for accessing data that's not bound to any AZ, such as metadata. As we can see, there are some limitations for placement policy and local transactions. So we introduced a new approach called local stale read. It doesn't need placement policy or local transactions. As mentioned earlier, when data is not bound to any AZ, placement policy and local transactions are not applicable. But we can find that we don't need to always read the leader. The follower replicas can also be read, although the data might not be the latest. Fortunately, sometimes strong consistency is not a must. So there is a chance where we can sacrifice consistency level to achieve low latency. So what is local stale read? It simply means reading the local replica, including followers. Since the data on followers might be stale, it reads stale data and does not guarantee non-usability. However, it still guarantees snapshot isolation, which is the key point we'll describe later. Let's take a look at the topology. When client in EZ2 visits TiDB node 2, the TiDB simply accesses the TiDB node which resides in the current AZ, even if it only has a follower replica. Here's an example of how to use local stale read. It joins the table users and the orders by the table ID. What you need to do is just specify a timestamp at the end of this statement. The semantic of this statement is the transaction reads local replicas, and it reads the same snapshot for the table and users and orders. The snapshot is not taken exactly at the specified timestamp. It may be newer. The snapshot cannot be stainer than the specified timestamp, and the transaction will read as new data as it can. Determining the start TS for the transaction is the most important part of this approach. The start TS has to obey to these rules. The first one is all data for the snapshot has been already replicated to the current AZ. Otherwise, the statement has to wait for the data, which causes high latency. And the second one is there should be no in-flight commits because they will update the snapshot later, which will break snapshot isolation. Let's see how it works. To determine the star TS, we need to maintain safe TS at first. Generally, safe TS is the commit TS of the latest data, which is replicated to all the replicas. Each reference group maintains a region-wide safe TS, and each TiDB instance maintains a store-wide safe TS. In this picture, there are 4 regions, and the store-wide safe TS is the minimum safe TS of all the regions. Then any snapshot after the store-wide safe TS can be read immediately. Then TiDB reports the store-wide safe TS to TiDB, so TiDB can maintain an AZ-wide safe TS. In this picture, the AZ-wide safe TS is the minimum of all the store-wide safe TS. Then any snapshot after the AZ-wide safe TS can be read immediately. Now it's very simple to determine the star TS for the transaction. TiDB can determine the star TS locally, so it doesn't need to visit the remote PD leader. The star TS should be no stater than the user specified timestamp, and it cannot be stater than the AZ-wide safe TS. So the star TS can be calculated easily. It's the maximum of safe TS and the stale TS. Now we have talked about all the solutions in TiDB. Let's have a brief summary. The solutions are suitable for different scenarios. When the data can be bound to any AZ, you can use placement policy to define the placement of data, and use local transactions to access local data. When you want to access global data, you can use global transactions. When the data is not bound to any AZ and you don't need strong consistency, you should use local stale read, which just reads local data. Both of these solutions can achieve low latency. If you want to know more information, please feel free to contact us through the website, GitHub, Twitter, or Slack. This is us. We are PinCap. We provide state-based solutions. And we are building TiDB, which is an open source distributed news circle database. If you have any questions, please drop them in the Slack channel. That's all for my talk today. Thank you for your time.